All right, today we're diving into a story that honestly feels like it's straight out of a sci-fi thriller, except it's very, very real. It's happening in hospitals all over the world. We're talking about a new kind of superbug, one that has learned some absolutely terrifying new tricks from two of medicine's most notorious enemies.
You see, for the longest time, medicine has been fighting two separate battles against the same bacterial family. On one front, you had the drug-resistant bugs that live in hospitals. On the other, these hyper-aggressive germs that pop up in the community. The chilling question we're all facing now is, what happens when those two nightmares decide to team up?
So our whole story here starts with this one bacterium called Klebsiella pneumoniae. But, and this is the important part, not all Klebsiella are created equal. Not even close. For a long time, we've really known about two very different versions, and each one has its own dangerous personality.
Okay, so think of it like this. On one side, you've got the bruiser. This is your caustic, tough-as-nails Klebsiella you hear about in hospitals. It's stubborn, and it's an absolute master collecting antibiotic resistance. Then on the other side, you have the assassin. This is the hypervirulent version. It's incredibly aggressive, and it can cause these devastating, life-threatening infections, not just in the sick or elderly, but in perfectly healthy people out in the community.
And this table just lays it all out, doesn't it? The bruiser, it hangs out in hospitals. It goes after the vulnerable, and its whole thing is drug resistance. The assassin, though, it roams the community, and its superpower is pure, raw aggression. But here's the key. Look at their weaknesses. The bruiser wasn't all that invasive, and, crucially, the assassin, you could usually kill it with antibiotics. For decades, these were two completely separate problems. There was a firewall between them.
But then, that firewall was breached. The bacteria, they figured out a way to start trading their secrets, to share their deadliest superpowers with each other. And this, right here, is where our story takes a very, very dark turn.
So how'd they do it? Well, to get how this works, you have to understand something called a plasmid. A plasmid is, and this is the best analogy, it's basically a genetic USB drive for bacteria. It's this tiny little loop of DNA, and it's separate from their main chromosome. And on it, they can carry genes for special abilities. And it's just like a USB drive. One bacterium can just pass it to another, instantly sharing the blueprints for things like antibiotic resistance or supercharged virulence. And this slide shows the two ways this whole nightmare scenario can go down. In one version, the super-aggressive assassin gets its hands on a plasmid full of armor, learning how to just shrug off our best antibiotics. In the other scenario, the already armored bruiser gets a plasmid packed with new weapons, learning how to cause those really devastating infections like its cousin. Either way you slice it, both paths lead to the same terrifying destination.
So what kind of stuff are we talking about on these genetic USB drives? Well, on the resistance side, you've got genes that can destroy carbapenems, and those are often our absolute last line of defense. And on the virulent side, you've got genes that create this thick, sticky shield to hide from our immune system, and others that build these little molecular machines to literally steal iron right out of our cells to fuel the bacteria's growth.
You put it all together, this genetic swap, and what do you get? You get the birth of a brand new villain on the world stage, CR-hvKP. It combines the impenetrable armor of the bruiser with the lethal aggression of the assassin, all rolled into one terrifying organism. And just look at how fast this all happened. It's kind of terrifying, actually. The first key resistance gene pops up in '96, but it really wasn't until around 2014 that we started seeing the first serious reports of these hybrid strains. And from there, it just exploded. Within 5 years, it was a global problem. And today, it's considered one of the most urgent threats we face in infectious disease.
So this new superbug, its arsenal is just, well, it's horrifying. It's resistant to our best drugs, it hides from our immune system inside this sticky shield, it starves our body of nutrients it needs, and it causes these awful infections that just spread through the body. We're talking liver abscesses, severe pneumonia, meningitis, even in people who should be strong enough to fight it off.
And don't think for a second this is just a problem in one place. This chart right here, it tells a really clear story. While yeah, a lot of the initial reports came out of China, this superbug has been found all over the world. It's in Asia, it's in Europe, it is in the Americas. This is a truly global threat.
Okay, so that's a whole lot of bad news. I get it. But it's not the end of the story, not by a long shot. Now we get to talk about the fight back, this global race to outsmart an enemy that is constantly evolving.
So, the big question is, how do we even begin to fight back?
What's the plan when science has to take on a foe that combines the worst of both worlds? Well, the battle plan has a few different angles. First up, surveillance. We're using these incredible genetic tools like PCR and whole genome sequencing to spot this bug the second it shows up. Now, treatment is tough. You often need a cocktail of antibiotics. But we're also exploring some amazing new options. Phage therapy, for example, which uses natural viruses to literally hunt and kill the superbug. And looking to the future, scientists are developing brand new drugs to disable its resistance armor or punch holes right through its defenses.
But out of all these strategies, the one thing that is absolutely crucial right now is speed. The faster we can identify that a patient has this specific superbug, the better our chances are of finding a treatment that actually works, and, just as important, preventing it from spreading to anybody else. Rapid detection saves lives, and it contains outbreaks. It's that simple.
And that really leaves us with the ultimate question, doesn't it? Bacteria have been evolving on this planet for billions of years. They are the undisputed masters of adaptation. We are locked in a constant arms race against this invisible enemy. As they keep sharing their deadliest secrets, building ever more powerful arsenals, the real question is, can our science keep pace?